Welcome to the course of Probability and Statistics. Today we are going to see what is independence of events. We are going to see the law of total probability, and finally Bayes' theorem. Independent events. The definition of independent events is that events A and B are said to be independent if the probability of the intersection of events A and B equals to the probability of A times the probability of B. From here, from the definition, we can prove that the probability of B equals to the probability of B given A, and the probability of A equals to the probability of A given B. This tells us that the fact that we know that an event has occurred does not affect the probability that the other event will occur. We are going to prove now from the definition the second set of equations we have about independence. So, if we know that the probability of A intersection B equals probability of A times probability of B, that is, events A and B are independent, we want to show that probability of B equals probability of B given A. In this case, we have to have that the probability of A is greater than 0, and the probability of A equals probability of A given B. So, for the first one, we have that probability of B given A from the definition of the conditional probability, that is equal to the probability of B intersection A divided by probability of A. From the definition of the independent events, we know that this is equal to the probability of A times the probability of B divided by the probability of A. And so, this is equal to the probability of B. The same way, for the second part, we have that the probability of A given B will be the probability of A intersection B divided by the probability of B. And so this is equal to the probability of A times probability of B from the definition of independent events. In this case as well, we have to have that the probability of B is greater than 0, is not 0. And so we have that this is equal to the probability of A. Now we are going to generalize the independence for two events, and we are going to see when three events are independent. So, events A, B, and C are said to be independent if the intersection of events A and B, the probability of the intersection of events A and B equals to the probability of A times the probability of B. Also, the probability of the intersection of events A and C should be equal to the probability of A times the probability of C. The probability of B intersection C should be equal to the probability of B times the probability of C. And finally, we should take the intersection of all three events. The probability of A intersection B intersection C should be equal to the probability of A times the probability of B times the probability of C. Let's see an example here. So if we perform this experiment, we toss a pair of fair coins and observe the outcome. We denote by A the event of heads on first coin. Also by B, the event of heads on second coin. We are going to see if events A and B are independent, and we have that for this experiment, A will be, the outcomes will consist from outcomes head-head and head-tail. We are going to write the sample space for this experiment, so we have it in mind. We have that S in this case, as we have seen before, will be all possible outcomes, will be head-head. We denote by H the outcome head, head-tail, tail-head, and tail-tail. Let's go back now to our example. So we have event A, which will be head-head and head-tail. Event B, which is head-head and tail-head. And we calculate the probability of A, knowing that the sample space consists of 4 elements. Event A consists of 2 elements. We have the probability of A, it's 2 out of 4. And the probability of B, again 2 out of 4. 2 elements out of 4 from the sample space. So we have that also the probability of A intersection B, which is the probability of the outcome head-head. We see that the intersection of these events is only the outcome head-head, the common outcome head-head. This will have probability 1 out of 4 to occur, which we know that it's equal to the probability of A. We have calculated that this is half, so this is equal to 1/4 as well. And so events A and B are independent. Now, we toss a pair of fair coins and we observe the outcome. We have event of heads on first coin, event of heads on second coin, and also the event of heads on exactly 1 coin. We now have 3 events. We have the events that we had before, A and B, and now we add up the event C. And we want to see now if these 3 events are independent. we calculate the probability of A, which is 2 quarters, the probability of B, 2 out of 4, and the probability of C, we see again that 2 elements in 4 from the sample space. So the question is if the events A, B, and C are independent. We first check if the intersection of events A and B, which is we have calculated the probability of outcome head-head, is 1 over 4. The probability of the intersection of the events A and C equals to the probability of the outcome head-tail, which is 1 over 4. And finally, the probability of B intersection C, again, is 1 over 4. We should not forget that although here we know that this is equal to the probability of A times B, and this is equal to the probability of A times C, and here this is equal to the probability of B times C, we need to check to take all three together as well. So we need to check if the probability of A intersection B intersection C is equal to the probability of A times probability of B times probability of C. Now, A, B, and C events do not have any elements in common, so their intersection is the empty set. And the probability of their intersection is the probability of the empty set, which is 0. In this case, we have calculated, we can also calculate the probability of A times the probability of B times the probability of C. We know that this number is not 0, is greater than 0, and so this probability is not equal to this one. Now we are going to work through an example to see how we can prove that some events are independent. So assume we have a standard deck of 52 cards. Standard deck, and we draw one card. Our experiment is that we draw one card. Event A, we say that we are interested if a king is drawn. B, the event that a spade is drawn. Now, we want to see if events A and B are independent. We calculate the probability of A that a king is drawn. We have 4 kings in the 52 cards, so we have 4 out of 52 probability of drawing a king. The probability of B, the probability that a spade is drawn, we have 13 spades in the deck, so 13 out of 52. And the probability of A intersection B, that is the probability that a king of spades was drawn, will be, we have only one in our deck, is 1 out of 52. So we see, now we compare with the probability of A times the probability of B, which is 4 times 13, 52 times 52, and this, if we do the calculations here, is actually 1 out of 52. So we can see that the probability of A intersection B equals to the probability of A times probability of B. And so the events A and B are independent. Now we are going to add another event, the event C, a king or a queen is drawn, and we want to see if events A, B, and C are independent. So I write again that the probability of A we have calculated is 4 out of 52. The probability of B is 13 out of 52. We have shown that the probability of A intersection B is equal to the probability of A times probability of B, which is 1 over 52. And finally, we calculate probability of C, which is a king or a queen to be drawn. We have 4 kings and 4 queens in our deck, so probability of C is 8 out of 52. And the probability of B intersection C, we calculate, is equal, we calculate the probability of drawing a spade and a king or a queen will be 2 out of 52. There is 1 king of spades and 1 queen of spades, 2 such cards in our deck. Now, probability of B times probability of C. From here, if we do the calculations, is 2 out of 52. So here we have, again, that probability of B intersection C is equal to the probability of B times probability of C. We also need to check probability of A intersection C, the probability of a king or a queen and A is the probability of, A is the event of a king. So this, here we have a king, here we have a king or a queen. So their intersection is actually, to draw a king is the event A, and this is equal to 4 out of 52. This obviously is not equal to the probability of A times probability of C. We say this is probability of A, not this. So from here we can conclude that A, B, and C are not independent. Here, if this equation was okay, if we're okay here, we should check the intersection as well of A, B, and C, the probability of the intersection of events A, B, and C, if it is equal to the probability of A times the probability of B times the probability of C. But in this example, as we found that this does not hold, this is not true, then we can stop. We do not need to check this. No matter what we find here, still events A, B, and C are not independent. Now we are going to see the law of total probability. Suppose A is an event and E1, E2, En are events which they have probability greater than 0. Their probability is not 0, and they are mutually exclusive events, and their union is S. Then we have that the probability of A equals the probability of A given E1 times the probability of E1 plus probability of A given E2 times probability of E2, and so on, the probability of A given En times the probability of En. We are going to draw a picture to understand the law of total probability. So if we have our sample space S, and we have mutually exclusive events, they do not have any common elements, and their union is S, so we have E1, E2, E3, and E4, then we want to calculate the probability of an event A. We can see from this picture that the event A consists of the area here, which is A intersection E1, the common area of A with E1, and the common area of A with E2, this part here, A intersection E2 and the common area here, A intersection E3 and this part here, A intersection E4. And so we understand from here that the probability of A will be the probability of this, A and E1, A and E2, or A and E3, A and E4. So this we see that are mutually exclusive events here, so we can add up their probabilities. We have probability of A intersection E1 plus the probability of A intersection E2 plus the probability of A intersection E3 plus the probability of A intersection E4. And this we know by using conditional probabilities is equal to the probability of A. We can write again what we had before to see how the conditional probability will be introduced. We multiply and divide by the same number. Here we have to have that probability of E1 is not 0, plus, and so on for all others. Probability of A intersection E4 times probability of E4 divided by the probability of E4. And from here we have that probability of this will be A given E1. We see that this part here will be the conditional probability times probability of E1, and the same way the rest of them, A conditional probability times the probability of E4. Now we are going to see an example to see how we can use the law of total probability. We have a machine which has a component that comes from 3 suppliers, A, B, and C. They come in the following percentages: 50% from supplier A, 40% from supplier B, and 10% from supplier C. We note here that, of course, we have, if we add up these percentages, we have 100% supply from all 3 suppliers. Now, the 3 suppliers produce this component, and the component does not work properly, 6% of the components produced do not work properly, 10% of supplier B do not work properly, and 15% from supplier C do not work properly. In this kind of examples, it is nice to use a tree to have a picture of the percentages, a picture of what's going on. So we have the component supplied 50% from A, 40% from B, and 10% from C. From the components produced by supplier A, 6% of them are defective and 94% non-defective. This is known either from past experience or having analyzed data. Supplier B produces components which are defective, 10% of them are defective, 90% of them are not. And supplier C produces 15% defective ones and 85% non-defective ones. Now, if we want to calculate the probability of the defectives, if the company doesn't mind from which supplier the component came, but wants to see what is the probability of having a defective component, then we can use the law of total probability. We can say that A, B, and C, denoting the events that the component has been supplied by supplier A, B, and C, respectively, are mutually exclusive events. One component cannot be supplied from supplier A and B at the same time, and their union makes our sample space S. 100% all of the components are supplied by suppliers A, B, and C. So the probability of a defective using the law of total probability is the probability of D given A times the probability of A plus the probability of D given B times the probability of B plus the probability of D given C times the probability of C. The probability that we have a defective one, a defective component, when it's supplied from supplier A is, as it can be seen here, 0.06. The probability that a component has been supplied by supplier A is 0.5. So we multiply 0.06 times 0.5. Then for this part, we look at supplier B. The component has probability 0.1 of being defective when supplied by supplier B times 0.4 probability of a component having been supplied by supplier B. We multiply these numbers plus the probability that the component is defective when supplied from supplier C, 0.15 times the probability that the component came from supplier C, 0.1. So we add up these numbers, we have that 0.085 is the probability of having a defective component, the company finds a defective component. Bayes' theorem tells us that if we have an event and again E1, E2 up to En, events that their probability is not 0 are mutually exclusive and their union is S, then we can calculate the probability of EI given A using this formula here. This formula, if we look at it, we can see that is actually, it comes from the law of total probability. Let's see an example here. We go back to the example we have seen before, and in this case, we want to calculate the probability of A given D, the probability that a defective component, which has been found, came from supplier A. Using Bayes' theorem, we see here the probability of D given A is 0.06 as before, probability of A 0.5, probability of D 0.085, and so 30 out of 85. So here in this lesson, we have seen what independence is. We have seen the law of total probability, Bayes' theorem, and some examples how to use the law of total probability and Bayes' theorem. For more information on this lesson, you can visit the web page of UNINETTUNO MedNetU project.